So, we were wondering about so many 2+ first excited states in even nucleus, and that too at energies smaller than what one expects if a nucleon pair is broken and taken to the next excited state. Right. Even nuclei, the ground state is always 0 plus. So, all the neutrons, all the protons are paired up. So, if you look for the excited states in that shell model structure, shell model scheme, you have to break one of those neutron pairs or proton pairs and take one particle in the next level. So, the energy needed to break the pair and then take the nucleon to excited state would be quite large, surely something like say 2 MeV, 3 MeV type. But in many of these even nuclei, we see the first excited state at about half of that expected energy. So, this is not coming from those excitation of nucleons in the shell model orbitals. So, some other kind of motion is involved in it. So, this is known as collective models, where you consider motion of the whole nucleus in one go on top of that shell model thing. So, you do have those orbital structures, the nucleons are going into those states, whatever S half and P 3 by 2, P half, D. So, all those levels are there. So, shell models is there, but on top of that the nucleus as such does some kind of collective motion. That is why it is called collective model. So, it is not one nucleon which is going from this orbital to that orbital or this level to that level, is the motion of the whole nucleus. So, that is why. So, how do we see these first excited states at 2 plus and other properties which come from these things? Okay. So, that is the topic. So, the kind of motions that a nucleus can have normally is divided in two parts. For many of the nuclei, you have vibrations of the nucleus, vibration of the nucleus shape, the surface. The equilibrium shape for these even nuclei, for most of them is spherical, most of them, not all. We will see which one have non-spherical shapes in equilibrium, but for most of them, say up to 150 at least, a less than 150, the even nuclei in their ground state, they have a spherical, nearly spherical shape. Now, this shape can vibrate, all nucleons can take part into it, and this shape, equilibrium shape remains spherical, but around that equilibrium spherical shape, the shape can change. So, as if there is some ball or something, if you squeeze from one side, normally it is spherical, but if you press from top and bottom, so it will bulge on the sides and it will become some kind of an ellipsoid, and if you squeeze from this side, then it will bulge on top and bottom. So, periodically if you do this, you squeeze it like this and then squeeze it like this. So, you will have a spherical ball, and then it is spread in this direction, pressed in this direction, then again when you release it, it will become spherical, and then you squeeze from the other side. So, this kind of oscillations in the shape can take place, and if you regard this as a drop in compressible fluid, then you can also see that how the shape of that drop will be changed. Now, shape oscillation can be in many different ways. This is squeezing and expanding in perpendicular direction is only one of the modes, but that shape vibrations can take place. So, if those shape vibrations take place, what kind of energies will be involved? If it is not vibrating and the nucleus stays spherical, then its energy is decided by that shell model levels. Then on that is ground state energy. On that, on top of that, if you induce these kinds of vibrations, then energy will be increased. Now, these vibrations are also quantized, right. We are talking at femtometer level. The size of the nucleus is in femtometers. So, at femtometer level, if some kind of oscillations, some kinds of vibrations are roped in, those will also be quantized. So, you will have one mode of vibration corresponding to one particular energy. You will have another mode of vibration corresponding to another energy, and these energy will be quantized. And if these energy happen to be less than the energy when one nucleon goes from this sub level to that sub level 5 by d 5 by 2 to f 7 by 2 and all that, then you can see these extra energy levels in between the shell model scheme, right. So, that is the vibration part of it. You also have a possible rotation part, rotation of a nucleus. The nucleus rotates as such. If it is a spherical shaped nucleus and if you try to rotate it about a diameter, then nothing changes. The configuration, the relative distances, separations, everything remains the same. But if it is a non-spherical nucleus and you rotate it about an axis which is not the symmetry axis of that, you can have different energies coming in. We will talk about that rotation part later. First, let us talk of vibrations, shape vibrations in more details. Okay. Now, if the shape is changing from spherical to non-spherical as a function of time, the shape can be described in terms of distance of a surface point from the center of the nucleus as a function of theta phi. If the surface is spherical, then at any theta phi you take a point on the surface, the distance from the origin is r, same everywhere. That is why it is sphere. Okay. So, if you have a spherical surface, as usual we draw a circle and call it a sphere in classrooms. Right. So, if you have a spherical surface, then any point on the surface you take, this point is on the surface, right, correct. It is not inside. I am not drawing point inside. It is a spherical surface and I am talking of a point on this surface. So, this distance is r, and if this r is same for all points, you say that it is a spherical surface. So, r, which represents distance of a point on the surface from the center, does not depend on theta phi. But if this sphere, if this surface is non-spherical, some other shape, then if you take a point on the surface here, you take a point on the surface here, you take a point on the surface here, at different places, this r will be different, and therefore, this r becomes a function of theta phi. So, depending on which direction you are from the center, which direction you are going and reaching the surface and asking what is the distance. So, it depends on that distance. So, r becomes a function of theta phi if it is a non-spherical shape. Now, any function of theta phi can be expanded in terms of spherical harmonics y lm theta phi, right, because y lm theta phi form a basis for theta phi space. So, any function of theta phi can be written as some linear combination of y lm theta phi, L going from 0 to infinity and m going from minus L to plus L. Since L and m we have reserved for that orbital angular momentum of the nucleus. We say that the spin parity is 0 plus, or in excited state is 2 plus, and this and that, and then we talk of this neutrons is in P3 by 2 state or H11 by 2 state. So, this H, that is L is equal to D, L is equal to, so that L and M, ML those symbols we will still be talking in terms of shell model. On top of that, this vibration is being attached. It is not an alternative to shell model, it is an addition to shell model. So, for this expanding in spherical harmonics, we will not write L and M, we will use another symbol lambda and mu. So, this can be any function can be written, therefore, this can also be written as summation over lambda going from 0 to infinity and summation over mu going from minus lambda to plus lambda in steps of 1, okay. And this is also in steps of 1, and then some coefficients, and then spherical harmonics. And if the shape changes as a function of time, that means for the same theta phi direction, this is the point on the surface and this is that distance r at theta phi. So, if there is oscillation in the shape, if the shape changes as a function of time, then in this expression what will become time dependent? These expansion coefficients, because these are standard functions. Whatever is the surface, whatever is the shape of the surface, that has to be expanded in terms of these standard y lambda mu spherical harmonics. These have standard functions like unity vectors I j k. Then if the particle moves, its position vector x I cap plus y j cap plus z k cap. So, I cap, j cap, k cap will remain the same, x y z will be function of time. So, these are like those unit vectors and these are the corresponding expansion coefficients. So, these will become time dependent, right. So, if this changes with time, then this will become time dependent. Now, if lambda is 0, what happens? For lambda equal to 0, for lambda equal to 0, this is y 0 and obviously mu has to be 0, because mu can only go from minus lambda to plus lambda, y 0 0, and y 0 0 you remember what is y 0 0 theta phi? It is just a constant, it is just a constant, no explicit theta phi coming in this. So, this lambda equal to 0 is, this is just a constant, this whole thing is constant independent of theta phi, and that means this is, it represents that radius of that sphere. The oscillations are around that spherical shape. If there are no oscillations, the equilibrium shape is spherical. On top of that, you have induced these oscillations. So, that radius of undeformed nucleus with spherical shape, that will be given by this lambda equal to 0. So, this term will just give you that average, or you can call it average radius. Similarly, if you look at lambda equal to 1 and put those 1 spherical harmonics with this 1 and mu here plus 1 minus 1 and 0. So, the standard expressions are there, right, in terms of cos theta, sin theta, e to the power I phi, etc., etc. So, from that linear combinations can be made, and when you look at that, that finally leads to a shift in the center of mass of the nucleus. So, the whole nucleus is going in one direction or the other direction. So, lambda equal to 1 corresponds to vibration of the nucleus as such, not the shape oscillations, center of mass shifting, center of mass vibrating, that corresponds to lambda equal to 1, and we are not interested in that. We are interested only in that internal motions. The nucleus as a whole, if it shifts, that is not going to give me the excited energy states. In the whole nucleus can anyway be taken here and there, that kinetic energy is different. So, for our consideration, the lowest lowest lambda which is important is lambda equal to 2, and then lambda equal to 3, 4 and so on. Lambda equal to 2, which is sometimes known as quadruple mode of vibration, will be something like which I was talking, you squeeze from one side and then squeeze from other side like that. So, you have a spherical shape, this is the equilibrium shape, and then the shape changes something like this. Something like this, then again it becomes spherical, and then it goes like this. So, this kind of shape oscillations, this will come from lambda by 2, sometimes known as quadruple mode of vibration. Remember, the center remains at the same place, it is only the shape that is changing. So, this will have its own energy levels and all that, and then you have lambda equal to 3, for which is known as octupole mode of vibration, and the shape at some particular instant will be something of this sort. So, bulging this side, bulging this side, bulging this side together, then pressed this side, pressed this side, pressed this side together. So, this is at one particular instant. Of course, it is changing its bulge and these dips as a function of time. So, this is the kind of vibrations in shape that will take place if you look at this lambda equal to 3 contributions, octupole. Okay. Now, if the vibrations are quantized, if quantum mechanics is operating, the energy cannot be changed in a continuous fashion. So, if you have some vibrational frequency omega that can also be calculated from the nuclear size and other parameters, then your energy could be h cross omega or 2 h cross omega, so on. And also, since this shape oscillation involves motion of the nucleon inside the nucleus as a function, and theta phi are coming into picture. So, they will also have orbital angular momentum corresponding to these shape oscillations. So, you will have energy corresponding to these shape oscillations, you will have angular momentum corresponding to shape oscillations. All this will be added to the shell model energy and shell model angular momentum and parity that is there because of those nucleons orbital motion inside the nucleus. So, it is on top of that, right. Now, it is easy to talk in terms of what quantum mechanics people called a phonon. If you set this nucleus into vibrations, you say that you have created a phonon, and the phonon energy here that is the energy of this vibrating nucleus. So, that is like h cross omega. Okay. So, either we say that the nucleus is vibrating and the vibrational energy is h cross omega, or equivalently we can say that this corresponds to creation of a phonon, a particle phonon with this much of energy. And if you go for the this is if it is in the lowest energy vibration mode with this quadruple mode of vibrations, it is h cross omega 1 phonon, and the next higher level corresponding to lambda equal to 2 only, corresponding to lambda 2 equal to 2 only, the next higher energy will correspond to 2 phonons, creation of 2 phonons. The shape will change in a different way now, but still the frequency, vibrational frequency will be the same omega.
Phonon have charge?
No, no charge. So, this is another way of talking of that vibration of the whole system, right. Classical physicists will just look at the whole lattice or nucleus or the system as a whole, how it is vibrating. That vibration thing itself is equivalently talked in terms of these particles phonons. Okay. So, this is one phonon, you can call it omega 2 if you like, to clearly say that this is the frequency corresponding to lambda equal to 2 vibrations. So, with this same frequency, when it goes into the next higher vibrational energy, we say that now you have 2 phonons, and then the energy is, so 1 phonon. So, let me write it again at a different place. So, 1 phonon of omega 2 or lambda equal to 2 type, this is the lowest energy vibrations corresponding to lambda equal to 2. So, you have a phonon, 1 phonon of this type, its energy is h cross omega, and its angular momentum quantum number is, give me some symbol, let us call it k, is equal to 2, because in quantum mechanics angular momentum is given in terms of this angular momentum quantum number. So, if I say k is equal to 2, that means the angular momentum is 2 into 2 plus 1 into h cross a square, square of the angular momentum is this much, right. The same theory, if I am talking of orbital motion, the angular momentum I describe in terms of small l. So, L is equal to 1, when I say, I mean the square of this orbital angular momentum is 1 into 1 plus 1 into h cross a square. So, it is the quantum number that we are talking of, k equal to 2, and the parity which is decided by this YLMs, lambda equal to 2 is even parity, right, just like that L, if L is even, your parity is positive. So, here lambda is even, so parity is positive. So, that is one phonon vibrations. So, in this, in other words, in this lowest kind of vibrations, lowest energy kind of vibration with lambda equal to 2, in that vibration the this angular momentum corresponding to that vibration, vibration of shape, not that whole nucleus is vibrating, that will be lambda equal to 1, that we are not considering. So, this vibration of this shape or oscillation of this shape corresponding to lambda equal to 2, quadruple mode, and with the lowest kind of energy involved, 1 phonon. So, for that the angular momentum is this much and the parity is this much. Then in this same lambda by 2 type, in this same lambda by 2 type, you can have 2 phonon vibrations, 2 phonons of lambda equal to 2 type. that will be higher energy, okay, that will be higher energy, and that will be 2 h cross omega. So, in that case energy will be 2 h cross omega is the same frequency as long as you are talking of lambda by lambda equal to 2 is the same frequency. Next mode of vibration with the same frequency. So, you have 2 phonons saying that the quantized energies are h cross omega, then 2 h cross omega, then 3 h cross omega. In this language we will say that 1 phonon is created, 2 phonons is created, 3 phonons are created, and so on. It becomes very handy, this phonon picture. Angular momentum of the nucleus corresponding to this kind of vibrations, right, because vibrations involve motion of all those particles, all those nucleons, then only the shape can change. So, nucleons have to flow from one side, go to other side to change the shape, and this motion corresponds to angular momentum. And this angular momentum, when you have this mode of vibration, will be obtained by adding angular momenta of these 2 phonons, and each of the phonon has angular momentum corresponding to angular momentum quantum number 2. So, it is 2 plus, or let us say 2, yes, it is 2 plus, parity is 2 plus, but angular momentum is 2 and another 2. So, you have 2 particles, 2 phonons, each with angular momentum quantum number 2, and you are talking of the combined angular momentum, right. So, 2 for first phonon, 2 for second phonon, and the combined system will have an angular momentum for which the quantum number will be from 2 plus 2 to 2 minus 2 in steps of 1. The same rule, if you are adding J1 and J2 and creating a resultant angular momentum, that quantum number will be from J1 plus J2 to J1 minus J2 or J2 minus J1, which one is positive, in steps of 1. So, that is the same rule here, 2 and 2, they will combine to either 4 or 3 or 2 or 1 or 0, 2 plus 2, 2 minus 2. So, 4 to 0 in steps of 1. But then you are talking of identical particles, 2 phonons, right, identical particles, this everything else is same. So, you have 2 phonons in, so you have to treat them as identical particles, and that we had done in previous lectures, previous lecture. 2 plus, we had added 2 and 2, 2 identical particles, and we have seen that the odd ones do not appear. Okay. So, this will give me 0 or 2 or 4, and parity is of course positive. Each phonon has positive parity, even if they had odd parities, if there are 2 of them together, this will become positive. So, these in this mode of vibration, the spin parity should be 0 plus 2 or 2 plus or 4 plus at this particular energy. Then similarly, you can go for 3 phonons. If you have 3 phonons, 3 phonon vibration, what will be the energy of this nucleus because of the vibrations, nuclear vibrations? 3 h cross omega, very good. So, you can have 3 phonon vibrations. Of lambda equal to 2 type, quadruple, we are still talking of that quadruple vibrations. Then you have energy will be 3 h cross omega 2, and angular momentum, that calculation will be more involved. That this 2 plus 2 giving you 0, 2 and 4 that we had done in previous lecture. On the same line, one can do the calculations, although the calculations will be much larger. And it turns out that all that angular momentum of 3 photons, 2 plus, plus 2 plus and 2 plus, that can give you 0 plus, 2 plus, 3 plus, 4 plus and 6 plus. Not easy to remember, only even one will come and odd will not come, that does not work here for 3. Why it is plus? There are 3 of them, 3 phonons, still the parity is plus. Each phonon has parity plus, it is lambda equal to 2. So, lambda equal to 2 corresponds to positive parity. So, you have positive parity into positive parity into positive parity. So, total is positive. So, and energy is going up, h cross omega, 2 h cross omega, 3 h cross omega, so on. If you look for lambda equal to 3, so vibration with this octupole mode, lambda equal to 3 vibrations, the first apart from 0, that first vibrational 1 phonon so 1 phonon vibration of lambda equal to 3 type. What should be the energy? Energy is h cross omega 3. Frequency will be different. Frequency for lambda equal to 2, lambda equal to 3 will be different, but it is 1 phonon. So, it is h cross omega. 1 phonon is just h cross omega. Okay. And what should be the angular momentum, quantum number corresponding to this vibration? Lambda equal to 3, lambda y lm theta phi, that L decides that angular momentum quantum number, y lambda mu theta phi. So, that lambda will be the quantum number. So, for 1 phonon it is just this, and what will be the parity? Plus or minus? Parity will be negative. Lambda equal to 3, odd, just like your p state has odd parity, right? F state has odd parity because L is odd. Similarly, here lambda is odd, therefore, the parity is negative. So, 1 phonon vibration of lambda equal to 3 type will give you 3 minus, spin parity 3 minus. You can have 2 phonon of lambda equal to 3 type and so on, energy will go up. So, if we are looking for that low lying energy states, yesterday that even nuclei that we were seeing, we were puzzled to see 2 plus, extra 2 plus coming in and some extra things coming in. So, the low lying energy levels, if you are looking at, this is enough, lambda equal to 2 vibrations with 1 phonon, 2 phonons, and lambda equal to 3 vibrations with 1 single phonon. So, that is enough for looking at those low energy things. Now, it turns out that this 1 phonon vibration, of course, the details will depend on which nucleus you are talking and all those, but on the average this energy of that same order as this 2 phonon lambda equal to 2 energy. So, this is surely lower, 1 phonon lambda equal to 2 energy is lower, and then you will have this energy and this energy, which is a different frequency now. So, 1 phonon lambda equal to 3 vibration, this energy turns out to be of this order, similar order. Here also, if we just look at this picture, then these 3 will have same energy, but there will be small variations. This is only an average kind of things that we are talking of. So, some variations will be there, but roughly if this 2 plus is coming because of this, so 2 and plus, so this is 2 plus, and remember it is in addition to the shell model angular momentum and energy of the nucleus. But even nucleus in ground state, that was 0 plus, and that energy we had taken as 0, right. So, it is 0 energy and the spin parity is 0 plus. On top of that, this is sitting. So, with 0 plus, if you are putting extra 2 plus, it will be only 2 plus. So, the final first excited state will come at 2 plus, that is what we had seen, we will see it again. So, or it is right on your screen, if you can focus on the screen, that 130 tin and 13 argon is there, and you have the first excited state at 2 plus. I will show more of these nuclei. All right. So, the first excited state 2 plus, that we were searching from where it is coming, that is coming from this one phonon vibration. Now, if you go up, you are likely to have 0 plus, 2 plus, 4 plus, and in the systematics I had shown some E energy of 4 plus divided by energy of 2 plus. I will show it again today, but this energy divided by this energy, what it should be? The energy here is 2 phonons, 2 times h cross omega, here it is 1 phonon, 1 times h cross omega. So, it should be around 2. So, you are likely to find this 0 plus extra 2 plus, extra 0 plus and extra 4 plus. We are still not talking of the energy because of nucleon pair breaking and going somewhere else, that is there, but below that you have these extra energies coming in. So, these kinds of level you might see in the energy level diagram at energy roughly double of this energy. Okay. So, the first 2 plus you will see, and then another 2 plus or 4 plus or 0 plus. So, in this now you focus on the screen and see that in 38 argon, for example, you have a 2 plus, you have another 2 plus, and you have a 3 minus also. This 3 minus might come from lambda equal to 3 vibrations, 1 phonon vibration. In tin also you can see you have first excited is 2 plus, and then roughly double the energy, and you have another 2 plus, another 4 plus, right. I will show you more of these kinds of energy levels. Okay. So, this is energy level diagram for, look at your screen. This is the energy level diagram for a 120 tellurium, and just do not look at this 4 plus. So, the ground state even nucleus is 0 plus, then you have this first excited state 2 plus, and roughly double the energy, you have 3 levels, 0 plus, 2 plus and 4 plus. So, where are these levels coming from? Which kind of phonons and how many phonons? These are 2 phonons of lambda equal to 2 type, that gives you 0 plus, 2 plus and 4 plus at approximately the same energy. You have a 3 minus here, but I am not sure whether it is coming from this level coming from here, or it is coming from the nucleon excitation, because now it is more than 2 MeV, but it might come from lambda equal to 3, 1 phonon of lambda equal to 3, and here you can see you have 3 plus, you have 4 plus, you have 6 plus, you have 0 plus, these ones. Yes, these are coming from 3 phonons of lambda equal to 2. So, 3 phonons of lambda equal to 2 type. This might come from 1 phonon of lambda equal to 3 types, and these are coming from 2 phonons. Okay. So, you can understand many of these energy levels. Here also this is 118 cadmium. So, you have 0 plus, then you have 2 plus, 1 phonon of lambda by 2 type, and you have these approximately double the energy, and you have another 0 plus, 2 plus and 4 plus, and then you have yet another 0 plus, 2 plus, 4 plus, 6 plus, 3 plus and so on. So, many of these low lying energy levels can be understood in terms of nuclear shape oscillations. This systematic I had shown you in the previous lecture. This is energy of this first excited state 2 plus. Okay. The energy, this is 1 MeV line, this is 2 MeV line. So, most of these are in this 1 MeV type range, and of course, you remember here these energies are extraordinarily small and these energies are extraordinarily small. So, we will talk about these things. Then I had shown this one. This is energy on of 4 plus state, first 4 plus state appearing from below, divided by energy of the first 2 plus state appearing below. Now that we know from where this 4 plus is coming, from where this 2 plus is coming, if in our model this ratio should be 2 phonons and 1 phonon of the same frequency, and this line is 2. So, it is around this, most of the time it is around this. Apart from this and this is A going from 150 to 190 and this is beyond 220. So, this is large, we had talked about this is large, about this ratio is about 3.3, but otherwise most of them are around 2. So, these are the systematics, and now we understand these systematics in terms of shape oscillations, why these are coming. Okay. Now, I am showing you yet another kind of nuclear energy level diagram. This is 174, what is W? Chemical symbol W, tungsten. So, the energy levels 0 plus is there, and the next one is 2 plus, next one is 4 plus, next one is 6 plus, 8 plus, 10 plus, and you see the energy separations are nicely increasing, and I have not given you the values, but these values are 100 kilo electron volts or so. This separation is some 100 keV. In the 1 phonon lambda equal to 2 vibrations, most of the time the energy was around 1 MeV, 1.5 MeV or 0.89 MeV, like that, around 1 MeV. Here it is around 100 keV, 0.1 MeV, at least 10 times smaller. So, this is another variety of energy levels that are seen in some of the nucleus. What is capital A here? Capital A mass number 174, okay. This is 174 W, and 174, remember on that systematic diagram, 174 lies in that 150 to 190 range here. Look at this, the energy E2 here 174 will be somewhere here. The energy of the first this 2 plus state is very small for all the nuclei in this range. 174 is a typical example, and all these nuclei will show the similar kind of energy level diagram. First 2 plus will be only at 100 keV, around 100 keV or 80 keV or 70 keV or 120 keV, it will be in kilo electron volts. Next will be 4 plus, and in the examples I had shown earlier, that 0 plus, 2 plus, 4 plus triplet, it was coming around the same energy and double of the first 2 plus. Remember, look at this 0 plus, 2 plus and 4 plus. So, this energy is around double of this first 2 plus, and then these are themselves they are close to each other. right. This will be true for all the nuclei which follow vibrations. This is 2 plus and then this is 0 plus, 4 plus and 2 plus. So, this energy these energies are roughly the same, these 3, and double of the first 2 plus. But the kind of thing now I am showing with this A equal to 174 thing, this structure is very different. This is 2 plus, then you have 4 plus here, then you have 6 plus here, and then you have 8 plus here, and then you have 10 plus here. So, this structure is very different. The energies are small, at the same time it is not following that pattern of vibrations. Another thing which is worth talking is this is systematic. This is on the y axis, we are showing the quadruple moment q of the nucleus. And quadruple moment, and this side is A, this side is A, and this point is 150, A equal to 150 is here, and this is 200, A equal to 200 is here, and these are the nuclei with A 150 to 190. And see, most of the nuclei, the quadruple moment is here, this is 0 point, this is 0 point. This side below that is negative, above that is positive. So, most of the nuclei up to 150 you can see the quadruple moment is small, but here the quadruple moment magnitude I am talking is much higher than the rest. So, these are a different class of nuclei. Then again you have large moment here at beyond 190, this is 200. So, this will be okay. So, here it is large, but focus on this. So, your 174 will be somewhere in this range. So, these nuclei are to be treated in a different fashion. They have some different kind of motion other than this vibrational thing. That vibrational thing is maybe there, but on top of that there is some other kind of motion which is present, which gives you energies something like 100 keV and so on, and the energy level diagrams is very different. This large quadruple moment compared to the most of the nuclei, this large quadruple moment tells that their equilibrium shape itself is not spherical. You remember, if you have a spherical charge distribution, the quadruple moment is 0. And any positive or negative quadruple moment tells you the deviation from that spherical shape of or the spheric or deviation from the spherically symmetric charge distribution, right. Spherically symmetric means if you have certain charge density at some theta phi, that same charge density is there for all theta phi, that is spherically symmetric. As a function of r it can change, but not as a function of theta and phi. Yes. So, that is spherically symmetric charge distribution, and in that case the quadruple moment is 0. So, for most of the nucleus you had seen that quadruple moment is small, that means their equilibrium shape is indeed nearly spherical, but these ones, of which this 174 is an example, the equilibrium shape is non-spherical. They are deformed to start with. Even in their ground state, their shape is deformed, they are not spherical, they are deformed nuclei. And if you have a system which deviates from spherically symmetric distribution, you can put in rotation which will change the configuration. If you have a sphere and if you rotate, nothing changes, it remains the same configuration. But if you have say a disc, take a disc, circular disc, and you have axis. So, about that axis you rotate the disc, nothing changes, but rotate the disc about a diameter, then the configuration changes. So, if you rotate such a non-spherical nucleus about appropriate axis, then you go for different kinds of configurations, and these rotations can bring in new energies, right. In quantum mechanics, these rotations are also quantized. The rotations are also quantized, and the rotation, the energy of rotation, energy corresponding to this rotation is related to angular momentum about that axis about which you are looking at the rotation. So, going in not going in details, but very basics. If you have a rotating system, the energy of that rotation in quantum mechanics, first classical mechanics, energy is given by half I omega square. Remember this formula? I is moment of inertia about that axis of rotation, and omega is the angular velocity of rotation. And if you write this in terms of angular momentum, what happens? L is I omega, that also you remember. So, this will be L square divided by 2I. L square is I square omega square, I square omega square. So, 1 I will cancel, half I omega square. So, if I take this as the starting point, and if you can give some symbol, but anyway we do not need it for long time. So, let me keep it L itself. So, you have L is equal to 0 and energy is remember L square, the value is L into L plus 1 into h cross square. So, L is equal to 0, energy is 0, no rotation, then L is equal to 1. What will be energy? 2 h square by 2I, right. 1 by 2I is there, and then L square is 1 into 2. L is equal to 2, it will be h cross square by 2I will be there, and then 6, 2 into 3, then L is equal to 3, h cross square by 2I into 12, 2 into 3, then 3 into 4, then L is equal to 4, the energy will be h cross square by 2I and into 20. This is general for any rotating system in quantum mechanics. These will be the energies in order of increasing order. But here, although the nucleus is deviating from a spherical shape, still some symmetry is maintained, which we call mirror symmetry. Nuclear wave functions are still definite parity states. So, if you have certain density, mass density at theta phi, then mirror reflect it in the origin, and you will have same density there. Okay. So, it is not random, any shape is not, although it is deviating from a sphere, but any shape is not allowed. So, you have this mirror symmetry, and when you impose that condition, then once again you find that only the even values of this quantum number are allowed. Okay. So, you strike out this and you strike out this, right. L equal to 5 you will strike out, next will be L equal to 6. So, if L is equal to 6, you will have h cross square by 2I and then into and so on. So, this is how you will calculate. And so, now on the shell model ground state of even nucleus 0 plus, you will be putting these energies and these angular momentum and these parities, right. So, this is anyway 0, fine. The first excited state will be L equal to 2. So, will be 2 plus. This 2 plus is different from that 2 plus, that is coming from the shape oscillations. shape is changing, and this is coming from shape is already deformed, but the whole nucleus rotates. So, this 2 plus is coming because of that. Next will be this 4 plus, and next will be this 6 plus, and next will be 8 plus, next will be 10 plus. So, now look at your screen. You have 0 plus, 2 plus, 4 plus, 6 plus, 8 plus, 10 plus, nice, very nice series. Now, look at the energies. 2 plus energy is at h cross by 2 I into 6. So, your first energy from 0 it goes here, and in the next the energy is 20, h cross square by 2 I 20. So, what is the ratio? Energy of 4 plus and divided by energy of that 2 plus, 20 by 6, 3.3. So, it is not double, that 4 plus will not appear at double the energy of 2 plus, it will appear at 3 times energy of 2 plus, and that is happening, right. It is not double, it is more than double, right. And next one will be 6, that will be 42. So, if I take this E of 6 plus divided by E of 2 plus, it will be 42 divided by 6, 7. Or difference you can see, this first difference is 6, and the second difference is 6 to 20, how much? 14, and the third difference is 20 to 42. So, the difference is continuously increasing, 0 plus to 2 plus, 2 plus to 4 plus, 4 plus to 6 plus, 6 plus to 8 plus, it will be continuously increasing, and that is what you are seeing here, the difference is continuously increasing. So, these deformed nuclei which have large quadruple moment, they will show you this kind of energy levels because of nuclear rotations, and these energies are quite low. So, we are still probably below that vibrational excitation, you are still in lambda equal to 0 mode. If there are vibration, it is still lambda equal to 0 mode, lambda equal to 2 vibrations will be at higher energies. So, if you only look at the lower energies, then for these even nuclei, deformed even nuclei, this rotational band will appear. Okay. And for the undeformed nuclei, you will have no rotational band, you will straight away start with the vibrations at larger energies around 1 MeV or so, fine. So, taking both ideas from the shell model as well ideas from the liquid drop model, we develop these type of collective models with which includes vibrations, oscillations and the nucleon excitations, and using this one can understand many of the nuclear properties of energy, spin parity, quadruple moment, this that quite well, all right. Fine.